Good morning, everybody. Welcome back to Physics Land. Okay, so we have 3 more classes. And in these classes, we're going to continue talking about Chapter 5. So where we are, we're talking about internal energy in microscopic systems. So we're talking about this randomized kind of energy inside of microscopic systems. And where we're going with this is that we want to be able to understand some things about energy that actually we don't have the tools to think about yet. And so here is an example of where we're going with this. So here is a question. You have a cup of hot coffee, a styrofoam cup full of hot coffee, or an insulated cup. Maybe you're more eco-friendly than that. So suppose that you have this cup of hot coffee in an insulated container and you put an ice cube in the coffee. You'd probably be extremely surprised if the coffee got hotter and the ice cube got colder, if energy flowed from the ice cube to the coffee. However, would this actually be a violation of the energy principle? So would this actually violate the energy principle? So most people said no. Some people said yes, and a couple people said that the energy principle doesn't apply in this situation. So let's think about these responses. So the correct answer is actually 2. It doesn't violate the energy principle, but let's see why. So first of all, the energy principle tells us that change in the energy of the system is the work done by the surroundings plus transfer of energy from the surroundings due to a temperature difference plus radiation absorbed. Okay, so because it's in an insulated container, we're going to say that there was no transfer of energy due to a temperature difference. The surroundings weren't doing work on this coffee and the ice cube. Nobody was stirring it or whatever, so that was 0. Negligible radiation assumed absorbed because it was an insulated cup. So we have that the change in energy of the system equals 0. Now, the energy principle absolutely does apply in this situation. It's a fundamental principle and it applies in every situation. That's the essence of a fundamental principle. It's always applicable. And so we're left with whether it violates the energy principle or not. And so all we have here is the change of energy of the energy of the coffee, and we're talking about the energy that's changing is thermal energy, right? Plus the energy of changing of the ice cube, of change in the ice cube equals 0. But there's no directionality in this statement. So this formulation doesn't tell us which way energy is going to flow. Now, we know that it is extraordinarily unlikely that the ice cube is going to get colder and the coffee is going to get hotter. But the energy principle does not rule that out. So it is not, this would not be a violation of the energy principle, and we have to look elsewhere to figure out, to understand why this is not very likely to happen. Likewise, the same situation Suppose you put your pencil on the table in front of you. Okay? Now we know that the atoms in the table, or the atoms in my hand here in the picture, are moving randomly. And of course, it's possible, there's nothing that rules it out, that they might all move in the same direction at the same time, so the pen will actually jump up off the table into the air. If all these atoms move up and hit the pen, and the pen jumps off the table into the air. This is not a violation of the energy principle. They could transfer kinetic energy to the pen, and it could jump up into the air, but it isn't very probable. Now, it also isn't a violation of the momentum principle. The change in momentum of the pen would be the force exerted on it by all the atoms in the table over the interval of contact. So these events, these possible events, would not be ruled out by our fundamental principles, but we know they're extraordinarily unlikely to happen. And so in order to understand what's happening, why they're unlikely to happen, we actually have to look at randomness at the microscopic level in order to understand what's going on. And what we're going to see when we do this is we're going to find out what this word entropy that you've all heard means, because it's deeply related to microscopic randomness, and why it's important in physical processes. And we'll think about whether we've actually got a new physical principle or not. So we think about randomness, we think about gas molecules moving around randomly in random directions and bumping into each other. And a simple mathematical model of randomness is what we call a random walk. And here what we've done is we've said we're going to restrict the motion of this particle, which could be a gas molecule or it could be a particle in a liquid, something like a red blood cell being buffeted by the solvent, or a lipid molecule being buffeted by the solvent, or it could be whatever. And we're going to say it, just to make our lives simple, we're going to restrict it to being able to move on a square, from point to point on a square lattice. And we're doing this in 2D just because it's easier to see, but you should think 3D. And so the rule is that every delta t, this object can take one step in a random direction, but there's only 4 directions it can go. So a random walk, this is called a random walk, and it's a mathematical thing that you can analyze. And the idea is that it flips a 4-sided coin, or it rolls a 4-sided die. Every time it has to move and decides which way to move, it moves completely randomly. So let's see what that looks like. So it would look something like this. So here's our particle that we're interested in, and it's moving around on this simple model of space. And it can move in various directions. But it's completely random. Okay, there's no rule that can tell you, no mathematical equation that can tell you which way it's going to go. It's just moving randomly. Okay, so that's what we mean by random motion. Now, if we have a lot of particles, what's going to happen here? So let's say we start in our model, we start these particles down here in the left-hand corner of our lattice here. And the rule is that they roll a 4-sided die, they can decide which way to move it. There's something already there they can't move. And so we'll let them go. And they're moving randomly. And it looks like this is going to take a while. So let's actually just speed up the program by increasing the rate at which this is running. So we'll go from a rate 20 to a rate 200. Okay, so and we can see that just by moving randomly, they spread out over very quickly over the entire volume that they're allowed to occupy. Now, in principle, because they're moving randomly, in principle, there's no reason that they might not at some point all end up back in that lower left-hand corner where they started. There's no rule that would restrict them from doing that. But it isn't very probable. Okay, we might have to wait a very long time before that happened. Now, so at the microscopic level, one of the things that determines the probability of events is just the fact that there's a lot of randomness going on. It is absolutely possible for the ice cube to get colder. There's nothing that rules it out. But we might have to wait a very long time before we saw that happen. In fact, we might have to wait for a time longer than the age of the universe before that actually happened, because it's just not very probable. And so this idea of randomness at the microscopic level gives us a measure, a way to think about the probability of certain events happening. So what we're going to be talking about today and for the next couple of classes is the consequences of randomness at the microscopic level. And what we're going to ask is questions like, we're going to be able to ask questions like the ice cube question, like suppose we as we did in chapter 7, we put two blocks together that maybe have the same heat capacity or maybe not, I mean specific heat or maybe not, and we let them sit next to each other in an insulated container, and we ask ourselves, what is the most probable thing we're going to find after we wait for a while? And it could be that this one is cold and this one is hot. It could be that this one is hot and this one is cold. It could be that they're at the same temperature. And none of this is impossible. None of these things are impossible, but it turns out that this is going to be the most probable. And we'll in fact be able to predict, we'll have some tools to be able to predict what's going to be the most probable outcome. So what we're going to talk about is not gas molecules diffusing, which is one kind of randomness. We're going to talk about random distributions of energy inside solids. Now, a solid, like the ball spring, the way we've thought about solids is a lattice of atoms connected by chemical bonds. A solid has the great simplifying property for us that every atom in the solid basically stays in the same place. It just moves a little bit. So we don't have to worry about randomness in the distribution of the atoms because they're all going to stay where they are. The thing that can randomly be exchanged is energy. And so in order to think about that, we're going to think about our ball spring model of a solid. So let's go back to that for a minute and review where we are on that. So remember that so by now this is a super familiar picture. We have these, there we go, we have our atoms bonded together by covalent bonds, which we model as springs. And we see that they're not static. They actually have some energy. Even when they get very cold, we still have some energy. And the energy is of two kinds. We would call it internal energy if we weren't interested, but it's in the details. But here it's energy in the springs, so spring potential energy and kinetic energy of the masses. So it's just a bunch of little mass spring systems, right? And because these are microscopic systems, we saw last time when we talked about energy in microscopic systems that not only were there discrete possible values of K plus U for atoms, systems of electrons and nuclei. In fact, a little oscillator, an atom bonded to something with a chemical bond, also had discrete possible energies. And so for this spring mass oscillator, this microscopic spring mass oscillator, of course, the parabola is the potential energy curve for this system. We found that it could never have less than a certain amount of energy, which we call the ground state energy, and that we could put energy in only in little increments, which we call quanta. And as we put in more energy, K plus U increases. So the maximum stretch increases and the maximum speed of the atom increases, and so we get, and that these possible energy levels, we call these quantized energy levels, in this system are conveniently, it turns out after you do the math, spaced in exactly equal increments. So the difference between any two of these energy levels is actually the same. Now, the model we're going to talk about here, we're going to actually simplify our ball spring model a little bit further. And we're going to talk about a model that was actually invented by Albert Einstein. And this is called the Einstein model of a solid. And so it's a ball spring model with a difference, which is he simplified it even further by saying every atom we're going to consider to be independent to move independently of its neighbors. So it's as if we had actually built a wall here around this atom. Okay? So we'd actually built a wall around the atom. And he said, furthermore, we're going to consider oscillations in the x direction as independent from oscillations in the y direction, which is independent from oscillations in the z direction. So we can put energy into oscillations in the x direction. And you can see even in this visualization, it's not quite right because it's stretching the vertical springs. But in this simplified model, this is completely independent and doesn't affect motion in the y direction. If you want to put more energy into the y direction, into y oscillations, you can do that. And then it moves up and down. Or you could put energy into the Z oscillations, and then it moves in and out. And in fact, to make this model really simple, he said, let's actually consider this a single atom as three different oscillators that actually aren't coupled to each other at all. One that moves in the X direction, one that moves in the Y direction, one that moves in the Z direction. And so this is, so every atom is modeled as three independent oscillators, as if it was connected to walls and it wasn't connected to atoms around it. And so that's the key simplifying feature of this model. Okay, so let's write that down. So the Einstein model of a solid one atom is modeled as three independent quantum oscillators. So we have one in the X direction with all its energy levels, and one in the Y direction with all its energy levels, and one in the Z direction with all its, and the energy levels are exactly the same. And the change in energy here, this is one quantum. And you may remember that it was h bar times omega, where omega is this oscillation frequency. It's the square root of the spring stiffness over the mass. In this case, this is the interatomic spring stiffness, and this is the mass of an atom. And where does this idea come from? It's actually kind of justified by the following thought. So we have the vibrational kinetic energy plus the spring energy is just going to be the momentum squared over the magnitude of the momentum of the atom squared over 2m plus the spring stiffness. But if we say that if we think of the stretch as a vector, where it's the stretch times L hat, our vector, in the direction of the stretchy spring, then we could actually write this as, well, p squared is just p sub x squared plus p sub y squared plus p sub z squared over 2m. And now this would be a half k sub s times sx squared plus a half k sub s sy squared plus a half. And so we really have the x part of the energy is completely separate from the y part. And the z part. So that's our model. That's what we're going to do. And one quantum of, so it basically looks like three independent oscillators. So this is really the important piece to keep in mind as we're doing this. And what we're going to do is think about this block of solid metal as a collection of these independent oscillators that can exchange energy just by emitting and absorbing photons. Okay, but that happens randomly, so the energy is exchanged randomly. So let's make this very concrete. What is a quantum? Well, let's consider a particular situation. Let's consider copper. We found that from Young's modulus, from stretching a copper wire, the interatomic spring stiffness turned out to be 27 newtons per meter. The stiffness of the interatomic bond modeled as a spring. And the mass of a copper atom is 1.06 times 10 to the minus 25 kilograms. That's the mass of a mole of copper divided by Avogadro's number. And our constant h bar is 1.05 times 10 to the minus 34 joule seconds. And so this quantum of energy, the difference between two adjacent energy levels here is going to be h bar omega. So it's going to be equal to 1.05 times 10 to the minus 34 joule seconds times the square root of 27 newtons per meter divided by 1.06 times 10 to the minus 25 kilograms. And we get 1.67 times 10 to the minus 21 joules, which is a really small number. It's equal to about 0.0105 EV. Remember the unit EV? So every quantum, when we talk about a quantum, we're talking about a real amount of energy. And for any specific object, we can figure out what that is if we know what it's made of. Okay. And it's going to be a different amount for lead or for aluminum or for some other. So what we're going to do here is we're going to think about the probability, the ways of distributing energy. So the number of possible ways of distributing energy, that's going to be the game that we're going to play for a while. And what we really want to work up to distributing energy between two objects that are made of lots of atoms. But for right now, we're going to look at the number of possible ways of distributing energy first in one object, and then later in two objects in thermal contact. So let's do something really, really simple. Let's take one atom, which is 3 of these oscillators. And let's say we have 2 quanta of energy. So we have 2 of these little energy packets, each one, let's say it's copper. So we have 2 little energy packets. Each one has that much energy, 0.01 eV. So let's think about the ways we could distribute this. So we could draw our energy level diagrams here. So this is the X oscillator, and that's the Y oscillator, and that's the Z oscillator. And we have these two quanta of energy. So pictorially, so that's two quanta above the ground state, right? We can't go below the ground state. So we could put two quanta into this oscillator, the x direction, and then there wouldn't be any left, so we'd have to have 0 in the y or the z direction. And we could, since we're drawing these pictures is going to take a lot of time, we can actually just call this, we'll just say, write down numbers 2, 0, 0. So that's one way of arranging that energy. And there aren't very many quanta, there aren't very many oscillators, so we can just write down all the possibilities. So let's do that. We could have 0 here and 2 here and 0 here. We could have 0 here and 0 here and 2 here. So this means we're putting both quanta into the same oscillator, and we have 3 ways of doing that. But then if we put one quanta into some of them, we could have 1, 1, 0, or we could have 1, 0, 1, or we could have 0, 1, 1, and I think we've run out. So there are really only 6 ways. Two quanta in 3 oscillators. Okay. Now there's some fancy names. These ways are called microstates. So microstate is just a way of arranging the energy among all the oscillators we've got. And the idea that we have 2 quanta in 3 oscillators, this is called a macrostate. So that's the constraint. We only have 2 quanta and 3 oscillators, and then there's 6 ways to do it. And the fundamental assumption of statistical mechanics and this is called statistical mechanics because we're doing probability and statistics here. And it's this, that every microstate corresponding to a given macrostate is equally probable and what that means is that if we had a way of taking snapshots of these oscillators and we took 1 billion snapshots, taking one every 10 minutes or something, we would find that 1/6 of the time we had 2 quanta in the X oscillator and none in the others. We would find that 1/6 of the time we had 0 in X and 1 in Y and 1 in Z. They're all equally probable. So let's consider a situation where we have 3 quantized oscillators, just like we had before. 3 oscillators, 1 atom. But this time we have 4 quanta of energy. So write down all the possible ways that you can find to arrange the energy. And so draw the pictures. I mean, write it down the way we did, 2, 0, 1, or whatever. They have to add up to 4, though. And figure out how many different ways there are to arrange the energy. In other words, how many different microstates there are for the macrostate. That means 4 quanta of energy in 3 oscillators. And I'll give you a couple minutes to do this because you actually have to sit down and list them all. So we have a question, were we going to learn to make an improbability drive like in the Hitchhiker's Guide to the Galaxy? And the answer is no, that's for an advanced course. Okay. All right, let's see what you said. And the most popular answer, just barely, is 4. And 4 is actually correct. So there are indeed 15 ways to do this. So let's see what they are. We'll write them down. We could put all 4 quanta in one oscillator. So we could have, there are 3 ways to do that. Or we could put 3 quanta in one and 1 and 0. So we could have 3 1 0, 3 0 1, 0 3 1, 0 1 3. Or we could have 1 0 3, 3 0 1. Wait, that's the same. We could have, let's be more systematic. Okay. We could have 3 in the second, so that would be 0 3 1 or 1 3 0. We could have 3 in the third, so that would be 0 1 or 3 1 0. So there's 6 ways to do that. And then we could have 2 2 0, 2 0 2, 0 2 2. So there are 3 ways to do that. And then we could have 2 1 1, 1 2 1, 1 1 2. So there are 3 ways to do that. So we get 15 ways to do this. Okay, so good. So now our 3 oscillators really would only be a system with only 1 atom, and that wouldn't be very. So the question is that just one macrostate? That's correct. There's one macrostate. So the macrostate is, the terminology here is, this is one macrostate with, we have 3 oscillators and 4 quanta. So the size of the system and the amount of energy in it is one macrostate. And there are 15 microstates, each of which is equally probable. And I only drew lines just to make it easy to add up, but there's 15 microstates, all equally probable. Thank you. Okay. So if we wanted to talk about a more realistic system, we'd want to have at least a nanoparticle, so at least 30 atoms. So think about a system with 100 quantized oscillators and 300 quanta of energy. How many ways do we have to arrange that energy? It is not as simple as multiplying quanta and oscillators. But we really would like to have a mathematical expression that let us do that, because when we get to this, we are not going to be able to write it all down. So we need math. Okay, so what math are we going to use? Well, it turns out that there's a probability formula that actually works. And so the formula looks like this. The number of ways of arranging energy, so the number of microstates, is equal to, and there's a symbol, we use the uppercase Greek omega as opposed to the lowercase Greek omega, which is angular frequency. And that's equal to the number of quanta plus the number of oscillators minus 1 factorial divided by q factorial times n minus 1 factorial. So q equals number of quanta, n equals the number of oscillators. So, and each oscillator is 1/3 of an atom, right? So let's see if this works. So we found that for 3 oscillators and 4 quanta, when we counted, we got 15 microstates. I'm going to use mu for micro. So let's see if that works. We find omega is equal to 4 quanta plus 3 oscillators minus 1 factorial divided by 4 factorial and 3 minus 1 factorial. So that's so what does this number come out to? This is 6 factorial on the top over 4 factorial times 2 factorial. Yeah, that's right, Parker. So, well, except there's the minus 1, so not quite. Yeah. So we have 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 2 times 1. And there's a little bit of cancellation we can do to make our life a little simpler, because this, that appears in both. And so we get 6 times 5 divided by 2 times 1, which is 30 over 2, which is 15. So we do get the right number. Okay, so how do you do this on a calculator? There is a factorial function on most calculators, but it actually it doesn't go far enough, okay? These numbers can get really big if you just evaluate all the factorials, and you get overflow in either a calculator or a computer if you do that. So there actually is a function in VPython and a function on your calculator probably that will do this. So in VPython, the function is called combin. And this is a very standard function name for any programming languages. So the number of the probability formula is called combinations. The combinations of some things taken so many at a time. And in VPython, combin of A and B is going to be A factorial over B factorial times A minus B factorial. And it's the same in Excel, actually. So we'd have to get quanta plus oscillators minus 1 factorial over quanta factorial times n minus 1 factorial, we'd write combin of q plus n minus 1. So that's what goes on top. That's A. And then B is either, we'll just write Q for B. On your calculator, so if your calculator is like a TI-83, if you go to math and then you pick math, there's math, numbers, something else, and probability. And you pick 3, which is NCR. So the syntax would be something like 5 NCR2. And it's a little different on an 89. Okay. So let's try this in VPython. So what was our question? We have 100 oscillators. So we have n equals 100 and q equals 300. So let's switch to VPython, which is here. And so we'll make a program and call it combin. Okay, so we have 100 oscillators and we have 300 quanta. And so the number of ways is equal to combin of q, let's see, q plus n minus 1 and q. And we'll print the result. And it's big. It's 5.6 times 10 to the 95th. So definitely not something we wanted to try to count on paper. And we're grateful for the help from probability theory. So very briefly, where does this come from? In probability, the idea of combinations has to do with picking from a set of objects in different groupings. So suppose you have 5 numbered billiard balls. In a bag. And you're going to pick them out one at a time. How many different orders can you pick them out in? So we have 5, 4, 3, 2, 1. And so you're blindfolded, you reach in, you pull out the first ball, and for the first ball, there's 5 possibilities. It could be any of those balls. For the second ball, there's still 4 possibilities. The third ball, there are only 3 possibilities. And the fourth ball, there's 2 possibilities in the last ball. There's only 1 ball left. So the total number of arrangements is going to be 5 factorial, because for the number of arrangements is going to be 5 possibilities for the first, and for each of those possibilities, there's still 4 possibilities for the second, and for each of those possibilities, there's 3, 2, 1. So that's 5 factorial, and that's 120 ways. And this is called permutations. These are permutations in probability. And that just has 120 different orders that are possible. But suppose you don't care about which ball, the number on the ball. Suppose you just care about the color. So suppose we have a bag and we have three red balls and 2 green balls. Whoops. Yeah, okay, so 3 red balls and 2 green balls. And if we're not red-green colorblind. Now, if all we care about is the color, then there's going to be fewer than 120 possible orders, because it doesn't matter if this is 1, 2, 3 or 3, 2, 1 or whatever. So if only care about color, fewer. And we could write them all down. So we could have red, 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 green, green, and we could have red, 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 green, green. Okay, so if we write all these out, we're actually going to get only 10 possibilities. And the way that plays out is that there's 5 factorial ways to pick the first ball, but 3 factorial of these are identical. Okay, so these are identical red balls. And the same thing, there's, you know, the 2 green balls could be 1, 2, or they could be 2, 1. So these are identical red. If we only cared about the green ones, the green ones, we don't care about the order either. So the number is really 5 factorial over 3 factorial times 2 factorial, which is 120 over 6 times 2, which is actually only 10. So that's the calculation we're doing. And in the book, there's an explanation of why this same formula applies to arranging quanta among different oscillators. And it basically comes down to sort of thinking of the oscillators as kind of stretchy bags. So here are our oscillators. And if we had 2 quanta in this one and 0 and let's see, let's not make it 0, let's make it 2, we had 1 and 1, then it would be the same as doing 2 quanta and a bag boundary, and 1 quantum and a bag boundary, and 1 more quantum. So these are boundaries. And so there's 3 oscillators, but only 2 boundaries between these. So that's where the n-1 comes from. Okay. So So all these ways of arranging things are equally probable. So microstates are equally probable. Macrostates are not. So if we go back to our two blocks here. Some arrangements of energy between the two blocks. So let's say we had 50 quanta here and 300 quanta here of energy. So the amount of thermal energy that we've got in these two blocks. So this is a macro state. And that may or may not be the most probable macro state for these blocks together. So what we're interested in is trying to use what we know about microstates to figure out what macro state is equally probable. That's the goal here. So let's think about the following question. So we have two objects, our two blocks, that share the total energy E, and this is internal energy, okay. And the total energy is the sum of the energy in block 1 and in block 2. So here's our blocks, block 1, block 2. So basically we take these blocks, and block 1 starts out with energy E1 and block 2 starts out with energy E2, and then we put them together. And the question is, how many different ways are there to arrange the total energy so that we end up with an amount E1 in the first object and amount E2 in the second object? So another way to ask this question is, if this is our macrostate with E1 here and E2 here, so that's our macrostate. How many microstates are there for which that can happen? Okay. So see, I'm asking you to take a little bit of a leap here. It's not something we've talked about, but see if you can think this through. How many different microstates are there? So you seem to be divided between adding these two numbers together and multiplying them. And okay, so that was a good guess. It was not something you knew. The answer is that in fact it is the product. So it's actually 150. And the idea is this, that there are 10 microstates 10 ways to arrange energy E1 in block 1. So for the first way, there's still 15 ways to arrange the energy in block 2. And the second way, there's 15 ways to arrange the energy in block 2. And the third way, there's still 15 ways. And so in fact, the total number of ways omega total is equal to the number of ways of arranging energy in 1 times the number of ways of arranging the energy in 2.